In this video, we will build a decision tree for linear systems. We'll build a decision tree which will help us determine the number of solutions of linear systems by looking at the corresponding augmented matrices in row echelon form. The first question in the decision tree is the rank of the augmented matrix equal to the rank of the coefficient matrix? Let's look at the takeaways that we had in the previous video. In the case of infinitely many solutions, we have that the rank of the augmented matrix is equal to the rank of the coefficient matrix. In the case of no solution, we have that the rank of the augmented matrix is greater than the rank of the coefficient matrix. And in the case of a unique solution, we have that the rank of the augmented matrix is equal to the rank of the coefficient matrix. And so it is in the case of no solution that we will answer no to that question in the decision tree. So is the rank of the augmented matrix equal to the rank of the coefficient matrix? If the answer is no, then the linear system has no solution. If, however, the answer is yes, then there are two options. Either the linear system has one solution, or it has infinitely many solutions. Now remember that both a linear system with one solution and a linear system with infinitely many solutions is consistent. And so if the rank of the augmented matrix and the rank of the coefficient matrix are equal, if the answer to this first question in the decision tree is yes, then we can say that the linear system is consistent. But in order to determine if the linear system has one solution or infinitely many solutions, we need to compare the rank of the augmented matrix with the number of variables of the linear system. So the next question is the rank of the augmented matrix equal to the number of variables? And so what have we found in our previous takeaways? In the case of infinitely many solutions, the rank of the augmented matrix is less than the number of variables. But in the case of a unique solution, the rank of the augmented matrix is equal to the number of variables. Going back to this decision tree, if the answer to the second question is yes, then the linear system has one solution. If, however, the answer is no, then the linear system has infinitely many solutions. In example 3.3.2, we're told that each of the following augmented matrices in REF was found by performing elementary row operations on an augmented matrix corresponding to a linear system. We want to determine the number of solutions of the linear system using the decision tree. And so we're given an augmented matrix in part A. We want to determine the number of solutions of the corresponding system. We first need to find the rank of this augmented matrix. What is the rank of the augmented matrix? Well, how many leading entries does it have? It has 2 leading entries. What is the rank of the corresponding coefficient matrix? It is also 2. And so therefore we can immediately conclude that the corresponding linear system is consistent, since the rank of the augmented matrix is equal to the rank of the coefficient matrix. Now we need to compare the number of variables with the rank of the augmented matrix. What is the number of variables in this case? It is 4. That's the number of columns to the left of the column of constants. So the number of variables is 4, which is not equal to the rank of the augmented matrix that we had found to be 2. And so therefore, the linear system has infinitely many solutions. since the answer to the second question in the decision tree is no. Now let's do the same thing for part B. For part B, we want to start by finding the rank of the augmented matrix. The rank of the augmented matrix is the number of leading entries, 1, 2, 3. The rank of the augmented matrix is 3. The rank of the corresponding coefficient matrix, in this case, is 2. And so the answer to the first question in the decision tree is no. The rank of the augmented matrix is not equal to the rank of the coefficient matrix. And so immediately we can conclude that the linear system has no solution. Moving on to part C, we want to find the rank of the augmented matrix, which is the number of leading entries in the augmented matrix. So 1, 2, 3. The rank of the augmented matrix is 3. What about the rank of the coefficient matrix? It is also 3. Therefore, we can immediately conclude that the system is consistent. But we still don't know if it has one solution or infinitely many solutions. We need to find the number of variables of the system. The number of variables is 3. And how does that compare to the rank of the augmented matrix? It is equal to the rank of the augmented matrix. And so therefore, the answer to the second question in the decision tree is yes. And so the linear system has one solution. Let's look at part D. Again, we want to find the rank of the augmented matrix. What is the number of leading entries? 1, 2, 3, 4. There are 4 leading entries, so the rank of the augmented matrix is 4. And the rank of the coefficient matrix is also 4 in this case. Therefore, again, immediately we know that the linear system is consistent. Now let's compare the number of variables to the rank of the augmented matrix. The number of variables is 4 in this case, which is equal to the rank of the augmented matrix. And so therefore, in this case, the linear system has one solution. Using this decision tree, we are able to determine the number of solutions a linear system has by examining the corresponding augmented matrix in row echelon form.